All right, so I'm going to ask that you take notes during this video because there are some really important ideas that I want you to have in your notes as we move forward. You don't need to write this first one down, but I think that it's a really interesting question. So we're going to introduce exponential functions today. Now, exponential functions can go really far. We've already been exposed to some of them, but we're going to introduce them at an Algebra 2 level today. And so I just want you to consider this really quickly. Will you make more money in option A or option B? And option A is you're going to receive $100 per day for doing a task for 30 days. Or if you choose option B, you will earn a penny on day one, and then each day for 30 days, it's going to double. You're going to double your money. So day one, it's a penny. On day two, you're going to earn 2 pennies. On day three, you're going to earn 4 pennies. Each day doubling. So take a moment, decide option A or option B. All right, so I'm going to just slowly reveal here. I have it written down, and we're counting cumulatively. So if you have $100 on day one, you have $200 on day two, $300 on day three, so on and so forth. So in option A, you make $3,000, but in option B, you actually earn $21,474,836.46. So really this seems a little bit deceiving, but in Algebra 1 you really talked about linear functions, and so option A is a linear growth model, whereas option B is something called exponential growth model, and it's one of my favorites, exponential. It's one of my favorite types of models because it actually models things that you have in real life. Car loans, house loans, credit cards, whatnot. So we'll explore this a lot more today. All right, so if you were to write an equation for option 1, for option B, this would be the equation. And what it's saying is you're starting with a penny, and each day, X, you're doubling the amount that you had before. We're going to get into how this all works, but really the premise, the form of an exponential function is y equals some initial condition or some starting amount on day 0 or 0 iterations, whatever, times the growth factor, the multiplier, and we call it the base. It's called B for base. And sometimes this will really determine whether it's growing or decaying. Now, an important thing that I would like you to write this down, so if you need to pause the video, please write this down, especially with the little arrows. But I also want you to remember an exponential property. Remember that if we're raising something to the power of -1, it really flips it into a fraction. So for example, 1/2 to the power of -1, it flips it. Well, if I have 1/2 to the power of -2, not only does it flip it, so we're going to do this one together, not only does it flip it, so it flips it to 2/1, that takes care of the negative, but it now needs to be multiplied by itself. So, 2 times 2 is 4, and 1 to the power of 2 is 1, so that ends up being 4. So just be aware that negative exponents flip it and then keep their value. All right, so we're going to do a growth model and a decay model. So I'd like you to graph this and make the table, and we're going to make the table together and then graph this one together, and then you're going to do one on your own. So to do growth, we notice that the function is f of x equals 2 to the power of x. And I want to be really, really clear about this. If we're using our format a times b to the power of x like we talked on the previous screen, the a value is 1, the b value here is this 2, and the a is 1, it's kind of invisible, it's 1 times that stuff. So I'm going to delete that just so that it doesn't get too confusing. But each time we substitute in, we'll do f of -2, that means 2 to the power of -2. Well, that flips it 1/2 squared, which is 1/4, or you could call it 0.25 just for convenience today. And you'll do this for all of them. So this is 2 to the power of -1, and the power of -1 flips it, so that ends up being 1/2 to the power of 1, which is just 1/2, or for convenience, we'll do 0.5. 2 to the power of 0, anything to the power of 0 is 1. 2 to the power of 1, so that's 2, so my output is 2. 2 to the power of 2. 2 times 2 is 4. So that's 4. My output is 4. So we'll go ahead and graph this, and we'll graph it in an ordered pair. So x, x, y. So negative 2 and 0.25. Negative 2 and 0.25. That's really, really low. I'm just estimating. I can't really get too much closer. I'm going to try and get a little bit closer. 0.25. It's really close. X is negative 1. Y is 0.5 or a half. Try and get that as close as I can to a half. 0 and then 1. 1 and then 2. 2 and then 4. If we kept going, 3 would be 8. And you can start to see, right? 3 squared, or excuse me, 2 to the power of 3 is 2 times 2 times 2, which is 8. So my output is 8, so we got 8 all the way up here. And you can start to see if we were to connect every point, this becomes this nice curve, and it would keep going forever in that downward direction, but it would actually have something called an asymptote. An asymptote, it's never going to become negative. No matter how big the number gets or how small the number gets, it's never going to be 0. It's always going to hover right near 0, but never get there as you go out and out and out. And you'll explore that a lot more now in pre-calculus when you take that course next year. Well, we want to talk about the domain. Well, the domain, if I'm thinking about all of the possible x values, it keeps going this way forever, it keeps going up forever. The domain is really all real numbers. So the domain is all real numbers because x can be anything, but the range is really limited. It has this asymptote. It doesn't go below, I drew that wrong. It doesn't go below 0. So the lowest value is 0, but it does keep going up forever and ever. It does keep going up and up and up and up and up. So the range is all values of y that are greater than 0. Now, it's never going to be 0, and then we've got our y-intercept. So we've got our y-intercept, which is, 0, 1, and that is obviously right there. So this one is a decay problem, and here, if I'm looking at my format, y equals a times b to the x power, my a here is 5, my b here is 1/2. So we'll go ahead and do what we did before again. So 5 times 1/2 to the power of negative 2. Now, I'm going to use a calculator for this one because I don't want to spend the time doing the computation and calculations. The really important part is that when you put it into the calculator, you put this 1/2 in parentheses, and you make sure that you're representing the negative 2 in parentheses as well. I'm going to go through and I'm going to fill all of these out, 1/2 to the negative 1, and then I'm going to pause the video and kind of fill them out with you. Double check that you can also get what I'm getting here in your output, because you'll need to be able to do that on your own. So just make sure that you can do that. You'll get out what you put in. So I'm going to pause the video and they'll magically show up for you, the outputs. So you should have gotten 20, 10, 5, 2.5, 1.25. And as you realize, as you look down this column, I hope that you noticed that it was getting cut in half each time. Well, hey, our multiplier is a half. A half, a half, a half, a half. We're multiplying each time x increases by 1. It's becoming half as much as it was before. Half as much as it was before. Half as much as it was before. Which is why this is called a decay, because as x gets bigger, it's decaying, it's getting smaller. So we'll go ahead and plot this on the grid, and we just want you to really understand where these numbers are coming from. So 2 and 20 is way the heck off my paper. So I can't even, negative 220, I can't even graph that. But I can graph 1, 10, right? Negative 1 and 10 is all the way up here. 0, 5, I can graph that. I can graph 1 and 2.5. I can graph 2 and 1.25. And I hope you start to see that this is going to come from way the heck up there, and it's going to also, ooh, I don't like that little divot that I made. So it's going to come down, and it's going to flatten out. It's going to get smaller and smaller, but it's also, if we go in this left direction, going to go up forever. So the domain, again, is all real numbers. Oops. All real numbers. The range is because it's the y values are always going to be higher than the x-axis. The y values are always going to be greater than 0. It's never going to be 0. But in this case, the y-intercept is 0, 5. Now, I hope you notice that A is the y-intercept. Just like on the previous slide, the A is the y-intercept as well. And that will be consistent throughout. All right, so go ahead and pause the video, and I want you to try this. Come up with it. I'll unpause the video when you're ready, and you'll see the answers just kind of magically appear. So please pause the video now if you haven't. All right, take a moment. I've only filled out the table. Make sure that you're getting these values in the table. And I want you to really pay attention. Hey, our y-intercept, when x is 0, our y-intercept is the a value, which is kind of handy, so we can even plot that one right away. I'm going to reveal the next piece here right now. And you can see that it's a decay, right? It's going down and down and down and down and down. And the domain is all real numbers. For this particular one, the range is all the y values that are greater than 0, and this has a y-intercept of 0, 4, the same as our a value. All right, we're going to transition here, and I want you to start thinking about word problems with exponential functions. So this is kind of part 2 of today's lesson, and the population, we're going to think about the application of exponential functions beyond maybe just the graphing aspect or the graphing component of something. So if a population of a large city was about 4.6 million in the year 2010 and grew at a rate of 1.3% for the next 4 years, well, on year 0, it's going to be 4.6%. And then on year 2, after 1 year, not only are you going to have the 4.6 million people, but you're also going to add, 1.3% of 4.6. So we're going to take 4.6 and multiply it. The decimal version of this is 0.013. We're going to multiply the population by 0.013, which is really, right, if we wanted to rewrite it in a, maybe kinder way, we would say this is 4.6 times 1.013. And we'll talk a little bit about what that is in just a moment. Well, if we did this again, we would be kind of multiplying, right? We're going to take this 4.6 and we're going to multiply it by, right, to go from the 4.6, we gotta go down twice. We're going to take that 4.6 and we're going to multiply it by 1.013 to get to the first year, right? And then we'll have to do it again, 1.013 to get to the second year. And really the fast way of writing that would be, and I'll try and do it in a different color, 4.6 times 1.013 to the power of 2, right? So we're taking that initial value and we're multiplying it by 1.3% twice. Well, if we do it again, we got to multiply 4.6 times 1.3% once because it's 3 years, twice because it's 2 years, and then one more time, 0.13. Sorry, I'm messing up the numbers. Well, once, twice, 3 times, which is why we have this term 3 times. So the number of years, we're multiplying it by however many years we're going. So on year 4, I bet you could predict that, kind of based on this pattern, 1 year it's 1, 2 years it's 2, 3 years it's 3, on this 4th year it's going to be 4.6 times 1.013. That represents a growth of 1.3% to the power of 4 for 4 years, where the starting amount was the 4.6 million. The growth, the multiplier is 1.013 to represent a growth of 1.3%, and the 4 representing the years. Now, in general, we could say, hey, what is the growth population in general? Well, we're going to take the 4.6 million, and that we're representing 4.6 million, so we don't have quite as many zeros, times the 1.013 to represent the growth of 1.3% to the power of n for the nth year, for n number of years. What that lets us do is we can predict any number of years, the population of any years. So let's say we want to know year 30. How many people are in this population after 30 years? So we'll substitute 4.6, 1.013, we'll substitute 30. And we're gonna need to use a calculator to determine the total number of people that happen in this space over 30 years. So 4.6 times 1.013 to the power of 30, I get 6.77, let's go out 3 decimal places, 777 population. But that's in millions, right? Million people over those 30 years. And we could do that for each one of these, find the population, and maybe that's a good exercise to do if you need to practice in your calculator. So I recognize this video is getting a little bit long, but I want you to take a moment to just kind of apply what you've learned, and I've already written the equation for you. But I would like you to answer these 3 questions, and they should be popping up on your screen anytime soon here. But this is the activity for today. All right, so a factory purchased a 3D printer in 2010, and the value of that printer is modeled by the function f of x equals 30 times 0.93 to the power of x, where x is the number of years since 2010. So if we were talking about 2011, x would be 1 because that's 1 year since 2010. So please take a moment to answer these 3 questions, and I'll let you read them for yourself just to kind of save on video. All right, so I hope you were successful in that activity. I want to talk, right, so like we've been playing around with this idea of this function, a times b to the power of x. And when things are growing, we've got this formula of y equals a times b, but if I'm talking about percentages, b isn't the percentage, it's 1 plus the rate, and the rate is represented by the percentage. So if it grows by 5%, the rate is 0.05. If it decays, then really we're going to take that 1 and we're going to subtract the r value where the rate is 0.05. So if it decays, we're subtracting the percentage as a decimal, and if it grows, we're adding the percentage as a decimal. So here are 2 situations. If something grows by 5%, our equation is y equal, I should do that in blue, y equals whatever the starting amount was, we'll call it a for now, but it'll be 1 plus 0.05 to the power of x. So simplifying, a times 1.05 to the power of x. Whereas if it decays by 5%, it's going to use this second formula, y equals the starting amount a, 1 minus the 5% as a decimal, and a times 1 minus 0.05 is 0.95 to the power of x. So you should be able to identify whether something is growing or decaying if the number is bigger than 1. So here we can tell that it's growing because the growth number, the b value, is bigger than 1. And in the right one here, we can tell that it is decaying because it is less than 1. So it's decaying because it's less than 1. Less than 1. And here it's growing because it's bigger than 1. So we're going to use this idea to think about it if you were purchasing a car and the value of that car, right? You purchase a car, and usually when you buy a new car, it's really expensive. And over time, like you drive the car, you use it, it loses some of its value. So if a car loses 20% of its value, but you purchased it for $24,000, the R value is going to be 0.2. because that is 20% as a decimal. So my equation is going to be y equals the initial amount, so 24,000, times 1 minus the 20% minus the 20% as a decimal. And so the equation is 24,000 times 0.8, because 1 minus 20% is 0.8, 0.8. So I'm going to use this equation to answer questions about the value of this car over time. So how much is the car worth 7 years after it's been purchased? Well, that means that x equals 7. If we were going to ask, like, after 10 years, then x would equal 10. So my value of my car is 24,000 times 0.8 to the power of 7. And I'm going to use a calculator, and my calculator tells me it is $5,033, and I'm going to round to the penny, so 16 cents, right? So the decimal keeps going, but, we're talking about dollars and cents, so I'm going to round it to the dollars and cents. So after, 7 years, it's not worth nearly as much as it was when we originally purchased it. So I want you to give it a try. If there are 220 hawks that were released into the wild in the year 2000, and it has a reproduction rate of 5% each year, think about it. Is the population increasing or decreasing? And I'll give this one away. Is it increasing or decreasing? Well, obviously it's going to increase because it's reproducing, right? We're going up. So go ahead and spend the moment to write an equation. How many hawks are there going to be in the year 2021? So that's 21 years later. And then really you might need to guess and check for part D. What year will it be when there are 280 hawks? I'm going to end the video here, and there should be a pop-up to have you enter your answer. Thanks so much for watching, and I'll see you in the next one.